So, hello everybody, I'm Quentin. I am a research associate at DLR, so at the Institute of System Architectures in Aeronautic in Munich. And I will give a presentation about prototypical control for the digital twin of aircraft environmental control system. And this presentation comes from the project Timafora, which is thermal management for hybrid electrical regional aircraft. And in this project, or at least in this project, we are focusing on the development of digital twin for virtual verification and validation. And on my side, at least I'm focusing more on the control part. Yeah, so let's start the presentation. So first, so as I said before, the project is called Timafora, so thermal management for hybrid electrical regional aircraft. And this project aims to develop a novel complete thermal management system for an hybrid electrical regional aircraft. And this presentation will focus on digital twin and mainly digital twin for virtual demonstration. And why then are we building digital twin? So usually when we want to demonstrate things, we focus, at least we do hardware test rig, because then we can test the real systems in real conditions and with all the real behaviors that happen in reality, noise, sensors, inaccuracy, and things like this. And then we get valid results that we can use for validation. But the problem is that those tests are usually expensive and takes a lot of time, and can also be dangerous. Let's say that this person is jumping from the cliff might be a bit dangerous for him. On the other side, one solution then could be to demonstrate the behavior of the system virtually. So we can do a full simulation of the system to then test the system in different configurations. And compared to hardware demonstration, we have a lot more possibilities because we can simulate whatever we want. So we can simulate one test case. We can simulate, in the case of an aircraft, we can simulate a complete flight mission in different and environmental conditions. So for example, cold day, hot day, or standard day. So yeah, a lot of things that you can do virtually. And it's also usually less expensive and less time consuming. But, and there is a big but, to make sure that we can use the results for validation, we need to make sure that the results are correct and are representing the behavior of the system. And that's the reason why in the project, it has been decided to do a combination of both hardware test rig and digital twin simulation for the VNV part of the project. And the idea is to do hardware test rig for components. So for example, we will demonstrate the behavior of a compressor or a full air or of a fan on hardware test rig, make sure that then it works as it is intended. And then this hardware test will allow us to validate the model of this compressor. And then we can implement the compressor inside our digital twin, knowing that the model that we use is a representative model of the component. And this demonstration is the one that has been chosen to achieve a TRL 5 demonstration at the end of the project for the complete thermal management systems of the aircraft. So in this presentation, we will focus on the digital twin part. So we will leave aside the hardware part because that's the task, because that's what DLR is tasked to do in this project. And the approach that we have chosen to develop this digital twin is the following. So the first thing that we do is that using Modelica and our library, the Thermo3 Stream library, we are building an initial digital twin model, which basically defines the interface of the different subsystems and how they communicate between each other. We also define simple and robust models to start showing the behavior of the systems and also to start having full simulation of the systems, also across a full mission. And even if the results are not representative, at least we know that we are able to run this kind of simulation. And that's the reason why the surrounding models are very important, and the controllers will be the main focus of this presentation. It's not about only having a good model for your components, it's also having the correct mission model, environment models, and also make sure that the controller that you are using is correctly controlling the system so that you can reach, for example, the desired temperature or the desired pressure inside the cabin. And then second step, once we have built this initial digital twin model, we will improve it. So the simple but robust model that we have developed will be replaced by high-fidelity models. Those high-fidelity models are developed by our partners inside the project, and then they share those models as FMU to the DLR, and we are tasked to integrate those FMU inside the digital twin. Once we have integrated the FMU, we have to validate that the integration is still correct, that the results are still conform to the initial results of the models. And once this validation step is done, we can do the proper virtual demonstration and then simulate the full system on complete flight mission for different test cases to get all the results we need for the virtual demonstration. So, as I said before, the main focus of this presentation is regarding controllers and why controllers. It's related to this step. In this step, we are integrating a high-fidelity model from the different partners, but this model takes time to be developed, and then they have to be validated with hardware tests, which also takes time. So we cannot wait to have those high-fidelity models ready before developing the rest of the digital twins, because it would be too late. So we have to do the development of the controllers and the development of the high-fidelity model in parallel. And then what we have done, at least in this presentation, the idea is to say, okay, since we are building simple but robust models, we can use those models to develop our controller. And then the idea is to develop the controller in order to make sure that we can use it to stimulate the high-fidelity model and make sure that our integration of the high-fidelity models is working. And maybe we will have to change the controller, but at least we can have a first idea of the system behavior and if our integration is working. So, yeah. But before focusing on the controller, I will give a short introduction regarding the model that we are considering. So, to develop this model, we are using our library, which is called the Thermofluid Stream library. It's a it's a Modelica library for modeling complex thermodynamic architectures, and it's very user-friendly, which is one of the main reasons why we are using it. Also because it's very robust, it prevents having nonlinear equation systems. And since we want to focus on the complete thermal management system, we want something that is robust so that simulation is a bit easier to do. So now let's have a look at the systems that we are considering. So in this presentation, we are considering an environmental control system for an aircraft. So the environmental control system is tasked to take air from the outside or from the engine if you consider conventional architecture, but in this case, we are taking air from the outside, and to pressurize and control the temperature of the air to make sure that afterwards, we get the proper temperature and the proper pressure inside the fuselage and at a given mass flow rate, because each passenger needs to have enough air during the flight. And finally, part of the air from the fuselage is expelled to the outside through the hose valve for the pressure control. Below, you see a picture of at least the Modelica implementation of the architecture that is above. And if we have a first look at the components here, if we start with the mission profile and the environment, since we want to demonstrate the behavior of the systems, we want to simulate our models for a complete gate-to-gate mission. So you can see the altitude and the speed profile. So we are flying from ground to ground with a cruise altitude of 20,000 feet. And we are also doing this mission for different days. So for standard day, 15 degrees on ground, hot day, and cold day. Afterwards, if we have a look now at the environmental control system itself, so it is made of two ECS packs in parallel. We have two ECS packs inside an aircraft because you still need to be able to, you need to prevent any failure or things like this. So the main reason is for redundancy. And the model that we are considering for this ECS pack is a conventional ECS pack. So usually ECS pack use air from, so this here is the fresh air inlet. So air that will be supplied to the cabin at the end. And in a conventional ECS pack, this air comes from the engine because it's already compressed by the engine and it's very hot. So there is a lot of energy available. So you can just use the energy that is already available thanks to the turbine to be able to control the temperature at this outlet. But since we are considering electrical aircraft, we have replaced the bleed air inlet by fresh air inlet. So it's only air from the outside. And since we still need to compress it, we have an electrical compressor here at the inlet to have the compression stage that is now missing. And afterwards, air from the ECS pack enters the mixer that you can see here. And here inside the mixer, air is mixed with recirculated air from the cabin, from the cargo bay, and from the avionics bay, and also from the cockpit, before being distributed into the different areas. And also here in the cargo bay, we have a split, and part of the air is released to the outside for pressure control. If we have a look at the cabin model, for example, here you see an example of the simple cabin model that we have built. So you can see it's only made of one volume, which represents the complete cabin with some heat load here representing, for example, the light inside the cabin, and some heat transfer models for the outside, for the solar radiation, for example, and also because of the outside temperature, so heat transfers through the fuselage. Since inside the cabin we also have passengers, then we have a passenger model that you can see here. So passengers are breathing air from the cabin and then breathe out air to the cabin again. And they are also producing heat. So everything enters this volume. And finally, as I said before, we have the outflow valve for the pressure control. Now that we have seen the base model, I can give you just a short example on how we replace those simple model by an FMU. So if we take the example again of the outflow valve, then we have our simple model above. And then what we do is that we get the FMU from our partners, and then we integrate this FMU using the component of our libraries to create an integrated version of this high-fidelity model. And then since both models are sharing the same interface, we can just replace it here and use the high-fidelity model when it is needed. Here you see the partners that are working with us on this system. So Honeywell is responsible for environmental control system, Fraunhofer for all cabin models, all cabin, cockpit, avionics, and cargo bay models, and Calling Aerospace for the outflow. So now that we had a look at our model, we can have a look at our prototypical control, which is the main focus here. So the system that I just presented, we want to control it at some set points. Those set points are mainly focusing on the cabin, so cabin temperature, pressure, and ventilation, and also the supplied the amount of fresh air that we supply to the passenger, because that's part of the certification. So from our models, we get we have some sensors inside the ECS pack and also some sensors inside the cabin, since we are trying to control the cabin conditions, and we can control the different actuators inside the ECS and also the recirculation fan and the outflow fan. But how do we build this control, knowing that we want to have this control robust enough and also compatible with either simple models or high-fidelity models here without having the high-fidelity models. To do this, we have defined three main requirements, so simplicity, adaptability, and robustness. So since we want something simple, we take a standard single input, single output architecture with API controllers and first order for the sensor. And for adaptability, to make sure that if the actuator model change between, for whatever reason, then we will normalize this command so that even if there is any change in this model, in the actuator model, then on the controller part, it doesn't change anything. Now, let's have a look at the different set points that we are trying to control. So if we start with the cabin temperature, for the cabin temperature, we don't have anything to do because our actuator is a valve, and the valve is directly controlled with a normalized signal between 0 and 1, 0 meaning fully closed and 1 fully open. So there is nothing to do on this part. And here on the left side, we can see the temperature control in the cabin for the different days for a full mission. We can see that for standard day and hot day, it's working perfectly. We can control the temperature of the cabin at 24 degrees for the full mission, but on cold day, it's not working. And this behavior is not related to the controller, but it's related to the model that we have chosen here. Because as I said, in a conventional architecture, we use air from the engine, and air from the engine is at 200 degrees. So we have a lot of heat available at the inlet of the pack. So the only thing that this pack needs to do is to cool air, because in any case, we want to cool. But for cold day, here, at least this pack takes air from the outside, and on a cold day, air from the outside is very cold. So we don't have to cool, but we have to heat. And in the conventional architecture, there is nothing implemented to heat the air, and that's the part that is missing here that would allow us to have a cabin temperature control also on cold day. Now, if we have a look at the ECS compressor temperature, so since we have compressors, we want to avoid having too high temperature at the outlet of the compressor, because then you have to size your compressor bigger, and also it will be more expensive, more heavier. So the idea is to use the Raman channel that you can see here in blue to control the outlet temperature of the compressor. But in the Raman channel, we have two actuators. We have a valve, and we have to represent the flap, and we have a fan to provide airflow on ground mainly. But in our architecture, we want to have one actuator, and the idea was to consider the Raman channel as one full actuator. And since we have normalized the actuator command, then we can just sum the two actuator commands. So instead of having a command between 0 and 1, we have a command between 0 and 2. And then we can just allocate part of the command to the flap, and then the rest of the command to the fan when it is needed. And by doing this, we are still keeping our single input, single output architecture. And you see, we are avoiding a maximum outlet temperature above 180 degrees. And on a cold day, again, we can see that what we are lacking is really heat here compared to standard and hot day. Now, if we have a look at the pressure mass flow, so we have to control the pressure mass flow to provide enough air to the passengers. And to do this, we control the electrical compressor, because that's why we have also a compressor here. And here there is the only thing that we have to take care of is that instead of directly sending the compressor speed, then we send a value between 0 and 1, and this speed has been normalized, and you just have to include the normalization factor in your compressor model if you change your compressor model. And now, if we have a look at the pressure control, so pressure control is again a valve. So it's like the temperature control for the cabin. There is not much to do in terms of architecture, and you can see that in any case, we can follow our set points for the cabin pressure. And finally, if we look at the cabin ventilation, so the idea is to have a constant volume flow at the inlet of the cabin for correct ventilation. So here, the idea is to have 50% fresh air flow from the pack and 50% recirculated flow from the cabin. Yeah, and so we can. That's why we have this target of 0.75, and we can control the ventilation at the target. So now, how we evaluate the robustness? Because the idea is that this controller should be compatible for both the simple model, but also for the robust model. So now we replace this initial ECS pack by a different version. So instead of having one turbine, we have two turbines and a two-stage expansion. This changes the dynamic of the pack. And now if we simulate our model again, then we don't have to change anything in the control. And we can see that we are still able to control the temperature with an error of 1 degree, which is completely fine according to the requirements. We can even make a comparison in terms of power, where we see that our second architecture is consuming less power for a normal day and for standard day and hot day compared to the initial architecture. So finally, what we had so far, we have built an initial model of the environmental control systems with working prototypical control that can be simulated for all flight conditions. And we have also validated that our controller is working for a different model, simulating the use of an FMU. But now what's need to be done is to actually use an FMU to see if it's still valid. And once we have done this, we just have to finish the validation to integrate all the FMUs, validate that the integration is correct, and then run the simulation for the virtual demonstration. So same comments. So I would just thanks Clean Aviation and the European Union, because this project is funded by European Union. And thank you for your attention.